presenting GenX today. I did not originally write GenX. I was just let's say power users until about a couple of years ago when I took over the project as it wasn't longer maintained by Mets who originally did it. And since then, I've tried to port it to the latest library versions and make some improvements that I personally would like and some that I got suggested from, for example, Andrew Karuna. Thanks for that. And because the paper is outdated, I won't show you anything. That's from 2007, but I will show you how to build that model. Because one of the improvements, or I hope it's an improvement, I made is trying to make an extremely simple beginner's kind of interface to build a model that's not so complex. And so at the beginning, when you start up GenX, you get this question, which kind of model you want to open up. And the normal old style interface would be the advanced reflectivity. The new one is simple reflectivity, or you can make empty models because GenX can in principle also work with any kind of Python scripted calculation. And if you want to show this on startup, you click this. Normally, you would probably stick to one interface. And when you use this simple model, building a new model is trying to, let's say, set you through the first steps of setting up the instrument in a wizard style. So we know this was a neutron measurement. And let's say I have this nice ortho version of the data that was supplied to us. The header is not up to the latest version, but this is just to show how this could look like. We have 4 columns, including a resolution column. So I say I want to use a ortho data loader. And the last step to define if this is an angular measurement or a Q measurement, which here it is Q. And then you see the main interface. So on the top left, you have a bunch area for data sets. So you can make one or more data sets that can be the same measurement, or it could also be X-rays and neutrons together and so on. Then in the bottom left, there's a plugin for storing materials. So you can have your typically used systems already in there and don't have to look it up again. On the top, you have the plots. So this is the model and the difference figure of merit when we would have data loaded. The scheduling length density. In GenX, it starts with a substrate or the backing material. So the surface is here now at 150. And then this is the new style of building the simple models, which is just one table for everything, where you have the ambient, the substrate, some number of surface layers. So you could add another one here, a number of layers that can be repeated. So now I have repetition 1, but this could be a multi-layer, and a number of layers that's below that. We only have 2, so I can remove that one. So to load the data, I select the data set and use this open here. And I select from the talk, which I have to look up. So this is the data set. I load it in. And now I want to build the model. So you have here for every layer, you have the option to either define it as a mixture of materials or by a formula. So the ambient here, as I was told, is silicon. So I just type silicon in here. On the right, you see the program analyzed that this is a silicon atom, and it found in the materials database that its density should be 2.3. And so if I press enter, here the density is directly put into the model. I do the same with the silicon oxide, which was also found. Obviously, I already put everything in there to make it easier. I call this oxide, and this layer I call, let's say, poly. The polymer, I don't know anything about the chemical composition, so I can enter just SLD into the formula, and then the value here is not density, but SLD. Let's say it's 2.7. I'm not a soft matter person, so I have no idea if that's correct or not, but we'll try to fit this. D2O, as the backing material. And that's basically the model. What we see, we're going far below the data because we didn't define any instrumental background, and also the scaling we didn't define. So I just used the mouse here to see what's the background level. So down here we see 3 × 10⁻⁷ would be the background level. And let's zoom in to the critical edge to estimate that. So that's something like 0.88. Then I go to this instrument settings where I get a dialog for the basic instrument options. Intensity 0.88, background 3⁻⁷, and resolution. As we have a resolution column, I only have to set a value that's not 0 to actually use that resolution. And I simulate it. It doesn't look too bad, but the thickness is obviously off. Let's try 250 angstroms. That's getting closer to 60, to 70. That looks quite nice starting point for a fit. So I select for fitting the 3 roughnesses, the thicknesses, and the density of the polymer. I start the fit, and you see the model improving. The figure of merit is shown above here. So that's a logarithmic figure of merit that's selected by default here. You can see at the bottom the speed of the simulation in simulations per second and the generation of the running fit. You can also see how this developed, and now we see at the last 30 or so iterations there's no real change. So we can basically stop the fit here. Now, if we want to get some more estimation about the error parameters, we should use an actual chi-square that has error bars. So to change the figure of merit, we can use the optimizer settings. Most of it can be ignored if you're not an expert, just changing the figure of merit from log to chi-square bars. And for that, we don't have to ignore nuns and infs, which can speed up the simulation. And also we increase the amount of parameters per population, because for such a simple model, it's just too fast and the GUI cannot follow anymore. So let's do that. And also limit min and max of each value so it cannot fit in any direction freely. And now if I run it again, you see that at the beginning of the figure of merit, things have changed because now the weighting is linear and with error bars. So let's fit that again. Now you see we are almost at a speed of 1,000. So basically 1,000 simulations per second because of the increase of the number of parameters per iteration. That's pretty much done. So we stop it. And then you can get a simple error estimation like this, where you get a nice list of the parameters that were fitted and their estimated errors. This is a quite rough estimation. It uses a 5% increase in figure of merit to get them lower and upper bounds. So this is not as rigorous as the statistical methods that Andrew already talked about. So now what we need to do if we want to get a bit more complex models, we have to use the standard reflectivity interface. Here is also an option to directly switch the model to that interface. So if you find out that this is not enough, you just click one button and you get back to the other interface. You can simulate again to check it's still the same. And now in this interface, we have first the parameter grid. That's the normal way to define what is fitted. Any parameter that is a floating point value can be fitted of the model. And the value here is shown with some bar about the position in its range. Here the ranges are set automatically from the simple reflectivity model, but you can modify them. Let's say we want the thickness of the oxide to not below 10 and not above, let's say 40. Then you see that the gray bar has changed a little bit. You can modify them either with the arrow keys. You can move them up and down, or with a mouse, you can scroll, or you can just enter the value. And you see nothing changes now because it's by default not set to automatically simulate again. but we can set this in a GUI here, simulate automatically. And now when I scroll, you see directly that the figure of merit and the values change. And I can also use this kind of slider view where you change the values like this. To get an idea how the figure of merit changes with the value, you can select one parameter and use this scan figure of merit. And then you get this graph and you see there are local minima for the thickness when you are at some points where some of the oscillations match again. Now, why we wanted to change to the more complex model, we wanted to constrain things. So the sample itself is defined here. You have a set of stacks that can be repeated or not, and each stack has a set of layers. Here for this model, this is simple. So let me remove all the stacks we don't need and just have one stack, 2 layers, still the same model. And now I want to constrain the oxide layer roughness to the polymer layer roughness. So first I remove the oxide layer from the parameter list here. And then here in the simulations bar, I can add function calls that are done before the simulation. And so here I can select, for example, the oxide layer, set the sigma value, and select from the polymer value the sigma value. And so these two are now constrained. You can make any kind of constraints between any kind of parameters, just have to be sure that these are not like circular constraints that would undo each other. And then we can run again the fit, which slightly changes the figure of merit again. And when I now calculate the error bars, you don't get the dialog, but you get it into the parameter grid. This is also how you can export it. And now if you want to go and be a bit more rigorous in the error calculation, thanks to the bumps library, there's an interface for GenX statistical analysis. The standard values are, let's say, good enough to get an idea, but you would need to increase the amount of calculations to get a better statistics. So I'm running here for 10,000 samples. At the bottom, you can see a rough progress to see how long it will take to get the results. And when this is done, this grid is filled with the covariance matrix estimation from the method. So normally this is the absolute covariance matrix, but you can normalize it by the 2 errors. And then you can estimate what are parameters that are correlated or anti-correlated. And then this plot shows you a set of 2 of those parameters. For example, here it is thickness of the polymer and thickness of the oxide. So this is here the a normalized covariance term is minus 0.7 almost. And when you look at less correlated, you see it's a more circular kind of shape. And positively correlated, you get a bit of a positive diagonal. And at the top, you have the estimated error values and the central values that came out of the Monte Carlo Markov chain Monte Carlo simulations. So now that we have that, another new option is to export it to the ortho data format, which is obviously in alpha because it doesn't really exist yet. And this exported data we can look at again. And now not only the header of the initial file is preserved in the data, but also the GenX name and version, the GenX script that is used, and all parameters, as well as the results of the Monte Carlo Markov chain simulations are added. And you have the raw data and the simulated data in this file. You can also access the information here with this info button. That's the metadata read from the file, which will obviously not be populated for all data formats. So you see the data source here contains that this, I guessed it was measured at platypus, and you see the sample name here containing the structure and some other information. And I think this was what I wanted to show. There's also a possibility to use a scripting interface that is relatively new. Where I also created a Jupyter notebook in our repository. Let's run all of the above. This is basically like building the model in the extended GUI, and it also includes some widgets for the Jupyter notebook. For example, if I have the model, I can have an interactive display of the model that, oh, no kernel. I think I didn't use it long enough, so the website cannot run it anymore. But here you can also do the fitting and do a bit more extended MCMC modeling and get the standard results that you can get plots with, that you can get with bumps. And that's my presentation. Do you have any questions?